let's prove the forward direction first. So assume that this is true. Assume A is a subset of B. And we want to show that this is true. We want to show that A union B equals B. How do we do that? Well, here's the thing. What is A union B? Well, that's just the same as the set of X such that X is in A or X is in B, right? Okay. But here's the thing. This condition right here tells us that whenever X is in A, X has to be in B automatically. So this whole part can then be simplified to just saying X is an element of B. Okay? Because whenever you're in A, you have to be in B anyway. So saying or, we can just simplify the whole expression to X is an element of B. Okay, so this is a set of X such that X is an element of B, which is just, of course, B. Okay, so this is true. Okay, so that verifies whenever this is true, this is true. Okay, but what about the converse? Let's prove the backwards direction now. So assume that this is true. Assume A union B equals B. And we want to show what? We want to show that this is true. We want to show A is a subset of B. How do we do that? Well, to show that one set is a subset of another, you say let X be a member of A, and you want to show that X is an element of B. Okay, and this logic, by the way, works even if one of these sets happens to be empty, because we're not guaranteeing there exists an element of A for sure. We're just saying if there exists something in A, then it also has to be in B. That's what subset means. Okay, so how do we prove this? Well, here's the thing. Since X is in A, that means X is in this guy, right? Because saying you're in this is the same as saying X is in A or X is in B, right? And so if at least one of these is true, this part's definitely true, then this statement has to be true as well. Okay, so X is an element of A union B, but what is A union B? Oh, look, we assume that it's just B. So look, X is an element of B, which is what we wanted to show. So that concludes the proof.